So hello everyone for this new 7th SIPTA Seminar of February, and we are very happy to receive Teddy Seidenfeld. We will speak about additive probabilities, and without further ado, I will leave the floor to Gerd de Koeman, who will chair the session.
Thank you, Seb. Welcome to this session. I was asked to say a few words about Teddy. And I'm very happy to do so. So I met Teddy during the first SIPTA conference in Ghent in 1999. He must have been a bit younger then than I'm now. So in that respect, I seem to have caught up with him. But there are many other respects in which it's difficult to catch up with Teddy. As I've said on a number of previous occasions, I consider him to be one of the greats in our field. And I know he doesn't like my saying so, but nevertheless, I think it's worth repeating it every now and then. So he has been and is one of the leading figures in imprecise probabilities, or indeterminate probabilities, as you like. And he's been at the forefront of many of the evolutions that we've witnessed in the past years, in the past 30 years. So just to sketch them, first wave IP, I call it first wave IP, where we looked at sets of probabilities and where it made sense to give meaning to the probabilities inside the sets. Then second wave IP, where we stopped looking at the individual probabilities in the sets and gave meaning to the sets themselves. And so where we looked at essentially at binary partial preferences to deal with uncertainty and decision making. And then the third wave IP, where we widen our perspective even further, the one we're currently in now, I think, where we deal with non-binary preference and with choice functions. Now, through all these waves, Teddy has been ahead of the pack. Asking annoying, asking difficult questions, keeping us honest and holding us to task. And through all these ways, in my mind, there has been one passion that never went away from him, the issue of finite versus countable additivity and the many unexpected repercussions that that issue has on many of the things that we do in imprecise probabilities. And if I'm not mistaken, this is also going to be on the table today. And I'm greatly looking forward to being amused, to being entertained, and to being challenged. So Teddy, you have the floor.
Well, thank you, Gert. This is a delightful occasion for seeing old friends, meeting new friends, and trying to interject one of my favorite hobbies, habits, addictions, however you want to think of it, relating to probability. I'll blame it on Finetti and Savage, who viewed it as an important theme that they came back to regularly about this mathematical question, whether probability needs to build in the infinitary properties of countable additivity or should be relaxed to permit other forms of quantitative probabilities that are not countably additive. I'll stick here with real valued probabilities. There's a whole other dimension, perhaps a richer dimension, that comes when you try and generalize away from the infinitary properties related to real valuedness. But here I want to resume a conversation or a discussion which I think was at the heart of Finetti's disputes with Kolmogorov, for example, about whether probabilities should be finite or countably additive. Just to advertise that what I'm reporting, good portion of it comes out of collaborations with two dear old friends and one new one, Mark and Jay. This was in fact our first topic of collaboration back in the very late 1970s. The brief anecdote here is Jay was giving a graduate seminar in the statistics department on the then relatively recent publication of Finetti's 1974 volume. And every week was a different chapter. By week 4, when we got to conditional probabilities, the audience consisted of 3 people, Mark, Jay, and myself. And we carried on from there every week now, almost every week for decades. The first topic we worked on was the conditional probability issues associated with finite additivity. I won't be dealing with that today, but this gives you a sense that for me, this is almost mother's milk of topics in terms of collaborations with Mark and Jay. Rafael who is an eminent, a very talented junior statistician. His father is well known also as a statistician. His father sent Rafael to study with Jay, and Rafael took his PhD at Carnegie Mellon under Jay. So this is also somewhat inbred discussion, but Rafael is an important contributor to our continuing debates on these topics. Let me give you a brief sense of what I'd like to talk about today. So the title is about probabilities and decisions. And the first topic I'd like to discuss is something which for me is relatively new information, though the material is not new. Mohammed Amr did this work 35 years ago, but I was blissfully ignorant of it. And when I came across it recently, thought that it should be given more advertising than I think it has received. So this has to do with arguments for taking finite, not countably additive probability seriously, in the sense that for certain kinds of mathematical structures, in particular familiar ones like basic logic algebras, you have no choice. If you want to put probabilities on these algebras, they must be merely finite, not countably additive. So the first topic I'll do is discuss that. Part two will discuss decisions driven by considerations that require purely finitely additive or non-countably additive probabilities. So the talk will have two parts. I've not done this before. I have no idea what the timing is, so we'll see how far I get. But I want to give you a preview of the fact that the first part will talk about issues of probability unrelated to decision making, whereas the second part will pursue issues related to coherence, which engage the finite versus countable additivity debate. So let's get going a little bit. So for the first part, let's just remind ourselves of the very basics of what the mathematics of probability is about if we're to discuss finite versus countable additivity. So we begin with this familiar triple of a state space omega, an algebra of events B. I will leave open what the details of the algebra are for a moment, and then a probability, which is either going to be finite or countably additive. To say that the probability is at least finitely additive is to say that for each set in our algebra, we assign a number between 0 and 1. The sure event of all possibilities gets 1. And if E and F are two disjoint sets in the algebra, their meet is the bottom of the algebra, then the probability of their union or join is the sum of the probabilities. This is the familiar finitely additive part. And the question is whether to add a condition that entails infinitary properties of countable additivity. There are two forms for this. The familiar form, which I think most of us run into, generalizes that third property about additivity on finite disjunctions of disjoint sets to countable disjunctions. And so if we have a denumerable partition of events into disjoint elements, then the probability of their union is the sum of the probabilities. This is the familiar version. The version which I want to emphasize today is an equivalent version, the way Kolmogorov gives it, equivalent given that the underlying algebra is at least a field, is that if you have a sequence of events that are monotone, either converging down or converging up, and their limit point is an element of the algebra, is measurable, then the probability is countably additive in the second sense if the probability of the limit is the limit of the probabilities. That is, you have this kind of continuity. And it's this version of countable additivity which I'd like to focus on today and use it to combine issues that relate the probability and the decision theoretic reasons for worrying about needing to drop this principle 4 in the form of 4b. So this is the unifying theme for today, is issues of countable additivity that are combined because we're concerned about 4b. Let me stop and check to see any questions, or have I put everyone to sleep already? No questions. Let's continue. So it's a bit of jargon. So we'll say P is finite, but if P is finite but not countably additive, it's merely finitely additive. That will avoid having to repeat finite but not countably additive over and over again. So merely finitely additive means it satisfies the first three axioms but not the fourth. And then there are flavors of being merely finitely additive. An extreme version is pure finite. Probability is referred to as purely finitely additive if in the first sense, with regard to violating principle 4a, you can find a partition, denumerable partition, such that the sum of the probabilities is less than epsilon. There's fixed epsilon, you can find a partition where the sum of the probabilities is less than epsilon. And then it's strongly finitely additive if in fact you can drive that sum to zero. So these two, purely finitely additive and a special flavor of purely finitely additive called strongly finitely additive, are extreme departures from the axiom of countable additivity. And we'll be talking about cases where you're compelled to use those kinds of extreme finitely additive probabilities. So in pushing for the need for finitely additive probabilities, if we're going to push to say that if you want to do something with something to be filled in, you're going to need one of these extreme kinds. Okay, Almer's result from 1985. So this is the most general of the results I saw in his two 1995 papers. And proposition 1, and this is already a bit of an eye-opener. So suppose we're dealing with an algebra which is an infinite free Boolean algebra. I'll give you examples in a moment which are simple and familiar. And his result is, which is valid, there's no problem with the proof, there are no countably additive probabilities on such an algebra. So if you want to put probabilities on such Boolean structures, they must be merely finitely additive. And in fact, the details are in the notes to the slides. In fact, every one of the probabilities that exists on this, and there are many, is purely finitely additive. So that's a small emendation, small sharpening of Almer's result, is that yes, not only can you not put countably additive probabilities on these algebras, but the only probabilities that exist on them are these extreme purely finitely additive ones. Let me give you an example to bring this home. So think of the Boolean algebra from your trainings in sentential logic, where you have and, or, not, negation, and the sentence letters as the atomic propositions, not atoms of the algebra, just the atomic propositions. The Boolean algebra is generated by this syntactic operation of taking ands, ors, nots, not with the sentence letters as the atomic propositions. The sentence letters form the generators for the algebra under those operations. To say that the algebra is free is to say that there are algebras in which all combinations of the generators, that is for each generator, consider the generator to be SI or not SI. You can take any finite combination of the generators, and the algebra puts the meet, the intersection of any finite one, strictly above the bottom, the empty set. That is, there's to speak in the semantic terms, if you take any finite sentence statement involving not a finite number of sentence letters, and you put not or leave it alone as SI or not SI, and take ands and ors, every finite construction of that sort is above the one sentence letter per one construction for each sentence letter. So you take, for example, a string of S1 or not S2 or S3 and construct any finite construction like that. It's below the tautology, which is the top of the algebra, and it's above the contradiction, which is the bottom of the algebra. So it's a free Boolean algebra in the sense that all these finite combinations take you between the top and the bottom and generate the whole algebra. So there are no constraints between the sentence letters. SI has valuation independent of SJ for all I and J. And the algebra is generated by all finite combinations of those sentence letters using ands and ors and nots. Is that enough of a working sense of the property of countably generated and free? It's the role played by the sentence letters and the fact that every well-formed formula involving a disjunctive normal form or a conjunctive normal form is with each sentence letter appearing only once in the construction, is above the bottom is not contradictory and below the top is not a tautology. The algebra is, the Lindenbaum-Tarski algebra for sentence logic is slightly more complicated. It basically takes the equivalence class of those expressions over logical equivalence. So if phi and psi are logically equivalent in this construction, they have the same position in the algebra. So this Boolean algebra is a free Boolean algebra in the sense that it is generated by all the combinations of and it's a countable Boolean algebra. It's generated by all the combinations of these countably many sentence letters, which are the generators. Now, the part that drives this surprising result about probability is from a feature of the algebra itself, and that's why this works. If you take a countable, so the algebra is a countable Boolean algebra. It only has countably many elements in it. There are only countably many well-formed formula in the logic. So of course, when you mod out by the equivalence classes, you have, of course, only countably many elements in the algebra. The algebra is oriented so that upward in the algebra is entailment, downward is, so if phi entails psi, psi is above phi in the algebra. So the bottom is the contradiction, which entails everything, and the tautology is the top, which is entailed by everything. So they play respectively the roles of the 0 and the 1, the empty set and the tautology, and the universal set. And the problem is we don't have sigma operations here because there are no infinite constructions in the algebra. No element of the algebra is infinitely long. So when you worry about joins and meets, you can say, well, which infinitary sets have joins, least upper bounds, or meets, greatest lower bounds? And what is quite interesting about these free Boolean algebras is that if you take, for example, let's take two sentence letters, S1 and S2. Their join is in the algebra, S1 or S2. Their meet is in the algebra, S1 and S2. What if I take infinitely many of these generators and ask, what's their join? Well, it's a countable Boolean algebra. There may not be one. But in the case of the generators, the infinitely many do have a join. There's a least upper bound to them. It's the top of the algebra. So if I take infinitely many sentence letters, all the sentence letters, and ask, what's their join? It's the top of the algebra. What if I take variations on those generators by replacing some of them with their denial and ask, what's the join of that infinite set? Top of the algebra. You're always pushed to the top of the algebra. So you begin to see that this algebra, because it's not a sigma algebra, doesn't allow you to put in the natural, what I would say the natural join, which would be the infinite disjunction, or the natural meet the infinite conjunction. You're forced to jump to the top or the bottom of the algebra. And because the algebra has that jump in it, any probability on the algebra has to jump along with it. And countably additive probabilities can't jump because of the continuity principle of the second version of countable additivity. You need a finitely additive probability to jump. So let me give you an example of this. I don't know if I'm making sense but maybe the following will help clarify it. This also comes out of Almer's work, the other of the 1985 papers. Let's think of the semantic interpretations of this algebra. If you assign a truth value to each sentence letter, you've interpreted the whole algebra. So give each sentence letter a value true or false. There are, of course, two of the Aleph Naught version, many variations of these. But any such semantic model will assign true or false to each sentence letter in our generating set. And of course, we'll assign a value true or false to each well-formed formula, each algebraic element of our algebra. So we're getting a two-valued probability. So for each element of the algebra, we get the value 1 as a probability if it's true and a value 0 if it's false. Consider the combination of sentence letters where each one has been assigned the value false, for example, under the model. So phi is either SI or not SI, depending on whether you've assigned SI the value false or true. So consider the combinations where each phi I has the value false under the model. Phi I being one of the sentence letters or its denial, the version that makes it false under the model. Then for every finite k, the probability assigned to the disjunction phi 1 or phi 2 or phi k is 0 because that disjunction is false. But if you ask what's the least upper bound to all of the phi I, there's no sentence in the language that reports it, but the greatest lower bound, excuse me, the least upper bound is the tautology, which gets probability 1. So here we see a rather dramatic illustration of the required jump that the algebra forces, because every finite disjunction of these phi i's is false, but their least upper bound, when you take the infinite set, is not the natural infinite disjunction. That doesn't exist in the language. Their least upper bound is the top of the algebra, the tautology, which has to have probability 1. So each one of these interpretations, every interpretation of the generators produces a strongly finitely additive probability, not just purely finite, but strongly, because you can construct the finite partitions, each of which has probability 0, and their limit point has probability 1. So I don't mean to spend more time on this now, except to say here, the algebra is compelling the introduction of the finite additivity, because the algebra has built into it this intuitive violation of the axiom for version B, because the continuity is already broken in the algebra. Where you want the infinitary disjunction or meet conjunction to go, it's not going there, it's jumping. It's jumping up in the case of disjunctions, and we could do the same thing going downwards. We could have a sequence of generators, each of which was assigned the value true. Their finite meet would be probability 1, but the infinitary greatest lower bound would be the empty set at the bottom. You jump down to 0. Let me stop here and see whether I'm making any sense. So, because I don't mean to say too much more about this, except to say that if you're dealing with probability on Boolean algebras, which are not sigma fields, and many logical Boolean algebras will not be sigma fields, not isomorphic to sigma fields, not even isomorphic to sigma algebras, as this example, you have to be braced for the failure of countable additivity that is built in to what I would call intuitively a discontinuity in the way the algebra handles greatest lower bounds and least upper bounds within the algebra. And sentence logic is already enough to compel it. So you take any logic that includes sentence logic, you cannot put countably additive probabilities over your whole logic. And of course, with quantifiers, we can do other variations of this. So let me stop and just see whether there's any question or discussion. There's something in the chat. What's in the chat? Oh, so Peter, did that give you enough of a sense of free and a free algebra? It's got generators, and all combinations of the generators keep you away from the top and the bottom. it's the least constrained algebra in that sense by the generators.
Yeah, Peter can't answer Teddy, so I assume that if he's okay, he'll put it in the chat.
Yeah, he's given up one way or the other. Either it's acceptable or hopeless, so we don't yet know which it is. Okay, so that's what I wanted to say about this first part. And I'll move on to the second theme, the decision theoretic theme now. Okay, so the second theme is the theme about where violations of countable additivity relating to this principle 4b, the continuity version, come in decision theoretically. And what I'd like to do is report on some results that relate to a 2019 paper that the four of us did on this theme. So I want to motivate discontinuities out of the decision theoretic side. And here I need to review a little bit of the decision theory associated with the failure of continuity that I want to emphasize. And so first I'll talk about three senses of dominance: uniform, simple, and admissibility or strict dominance, and then talk about the decision theories related to this and how finite additivity enters in trying to resolve some concerns of the admissibility kind, the strict dominance kind, which mimics Wald's use of admissible decisions in statistical decision functions. So let me just illustrate the principles here. So we now have a denumerable partition, and we have acts thought as functions from this partition to a set of outcomes, and we at least assume the outcomes may be preferred vertically within each state. And so uniform dominance says Act 1 is uniformly dominated. Act 1 uniformly dominates Act 2 in the sense that there's some fixed amount. We can say that every outcome in the first row is strictly preferred by the outcome in the second row by a fixed amount, at least epsilon. So we'll need to be able to talk about the difference in strength of preference, but we'll be using numerical values to represent outcomes and strength of preference of outcomes in this sense. So we'll be able to argue that each outcome in Act 1 is strictly preferred by outcome in the second row by at least an amount epsilon. So this is the bounded away dominance. The reason I emphasize this is because in Finetti's theory, the sense of coherence that's used requires that you respect uniform dominance, but neither of the other two following senses of dominance. So it's this more restrictive kind of dominance which makes up the core of Finetti's coherence theory. Simple dominance would just be that for each element in the partition, the second outcome, the bottom row outcome, is preferred to the top row outcome. And then the sense of admissibility, which is associated with Wald's work in statistical decision functions, is admissibility, is strict dominance, sometimes called Shimoni strict dominance, is that for each outcome in the partition, O2 is at least, the second one is at least as good as the first, and for at least one state, it's strictly preferred. And we have these three senses of dominance. The issue, which looks like a problem in finite additivity, problem in the sense that the finitely additive theory only takes us as far as the initial partition, initial weak bounded away dominance. And the illustration which shows this problem is this example here, which is in fact due to Finetti. So we have two random variables, two numerical valued quantities, x and z is the constant 0, and x is -1/n for state omega sub n. So that's this road. X is paying off -1/n, z is paying off 0. And if we put a purely finitely additive probability, which is 0 on each state, there are many different probabilities that do this, because I'm only telling you about the probabilities of singletons. And there are many different finitely additive probabilities that will put 0 on singletons. They differ in what they do on infinite states, but we don't need that for this dominance. You will see that in terms of dominance, the middle dominance principle, the simple dominance, is violated by the finitely additive expectations, because the expected value of x is 0. Because with probability 1, you're getting a value bigger than -1/n, but less than anything positive. So the only real value place that you have, the only real value you can assign to x is 0, because we don't have infinitesimals. This would be a way to open the door to non-Archimedean preference, but here we're still dealing with real valued preferences, and there's only one place to send the value of x with respect to uniform dominance, and that is to violate simple dominance and to give x the value 0. So this looks like a bug. This looks like a failure. But as I've learned living at Carnegie Mellon, the thing to do with failures, bugs, is to make them into features. And so that's what we're going to do next. We're going to learn not only to live with this, but to like this. Although other aphorisms here would be making lemonade from lemons. So let me turn this result on its head and show you what we're going to do with it to make it work in our favor. So let's suppose that there's only one state omega, and we're faced with this problem of choosing a prize from the half-open interval 0 to 1. So every act gives us a numerical value between 0 and 1, but not including 1. So it's the half-open interval. Every pure strategy is uniformly dominated because there's only one element in the partition. For every option, there's a better one. So there's something that's better by a fixed amount. Moreover, every countably additive probability over this space has an expectation strictly less than 1. I mean, each will be less than 1. So there's nothing to be done in terms of respecting even bounded away dominance in this case if we're dealing with countably additive probabilities. But, and here's where we take the bug and turn it into a feature, if you let P be a finitely additive mixed strategy, where you're assigning for each epsilon a probability 1 to x greater than 1 minus epsilon, that is, use a probability that pays off, for example, in state n, 1 minus 1/n, and put probability 0 on every one of those mixing states, then you have a random variable who has expectation 1. So this purely finitely additive probability gives you a value 1, even though there's no outcome that's as good as 1. Now, let me say that again. So we have a random variable, which is obtained by using a finite, purely finitely additive, strongly finitely additive mixture that's concentrating on the x's arbitrarily close to 1, 1 minus 1/n, put all the probability greater than 1 minus 1/n. Its expected value is 1, which means in this theory, that mixed strategy is just as good as getting the value 1, which is not available. It has value 1. So this is the bug which I've now turned on its head and made into a feature. And we're going to use this feature to solve a lot of open questions, difficult questions in the theory of statistical decision functions. So let me stop here and just make sure everyone understands that we all see the rabbit being pulled out of the hat and understand what kind of maneuvers, I expect I'm going to be doing maneuvers with this to solve certain problems in statistical decision functions. Any questions from the chat? I see no more questions from the chat. Okay, keep going. So some jargon. So if you have learned your statistical decision theory from Wald, and this is embedded in a lot of contemporary statistics, there are pure strategies or actions. There's an uncertainty space, often parameterized states of natures. And there's a loss function, which is formulated in terms of quantities of loss. The best you can do is 0, and typically, but not always. And losses are negative utilities. We'll make them negative cardinal utilities. A mixed strategy is, of course, using a probability to choose a decision, a choice. And risk is an expectation of loss with respect to elements of the partition. So it's not a Bayes setup in the sense that there's no prior over the theta. There's just the loss relative to each value of theta. So we're doing risk as the value of the outcome of the decision relative to the partition induced by theta. And a mixed strategy will just be a mixture of these pure strategies, but we'll allow ourselves to use finitely additive mixtures. And that's where we're going to depart from Wald and channel Wald through Finetti. Let me give you an example which will carry the bulk of what I want to say in the next part of this. So I want to use Breyer's score as the loss function. This also will allow us to connect up, for those who are interested in the literature on the burgeoning literature on philosophical measures of accuracy and so on. Proper scoring rules play the role of accuracy measures in that literature. I want to use Breyer's score. So the idea is that there's a binary partition, B and B complement. There are no data in our problem. You're just producing an estimate or a value for the indicator for B and for the indicator for B complement. So you have to forecast both B and B complement. You would expect to have values that sum to 1, but this will be a consequence of the theory. And so you're asked to produce a forecast for the event B and a forecast for the event B complement. And we're using Breyer's score for each forecast and taking sum of squares, sum of the Breyer scores as your composite loss function for each theta. Theta has only 2 points. It's either B or B complement, and you're forecasting both random variables, both indicators, and taking sum of Breyer's score. Now, the only admissible actions are, it's not hard to prove, the only admissible actions are probability forecast. You have to produce a value A1 for the forecast of B, A2 for the forecast of B complement. These are non-negative and sum to 1. That's a feature of this admissibility. Let me give you a picture of what I'm talking about here. So the black zone are the loss functions, depending on whether it's a two-dimensional loss function, because there's the risk set, the partition is binary, and you're forecasting both random variables, so it's a sum of squares. And the black zone is the set of risk values associated with pure strategies as a function of whether it's in coordinate 1 state B or in coordinate 2 state B complement. But remember, you're forecasting both states in each forecast, so it's sum of squares. So the admissible functions here are the lower boundary. Why? Because any point off there is either, so with regard to this point on the boundary, any point to the northeast is paying off worse in at least one coordinate and not better in either. So all points in the region above the lower boundary are inadmissible, and everything on the lower boundary is admissible because there's nothing that is to the southwest of it. And these are, and only these are the admissible forecasts, which turn out to be the probability forecasts, just what you would expect under squared error. So for example, 0.5 forecast will give you that loss function under Breyer's score. You're going to lose 0.25 for each of the forecasts in each state, and so you're losing 0.5 for the forecast of both random variables in state B and the same in state B complement. That would in fact be the minimax estimator, because that minimizes maximum loss. Anywhere else on the lower boundary, one of the coordinates is bigger than 0.5. But the Bayes solutions are all the lower boundary. And this is an illustration of what Wald was after, which was what would be the set of, what would be the minimal set of complete admissible strategies. That is, let me give you a bit of jargon here. Whoops, this moves into a different version of it, but the complete class, a set of strategies is complete if anything outside the class is inadmissible relative to something inside the class, and is minimally complete if no proper subset is complete. And here you get an instance of a famous result of Wald, which is the kind of result we're aiming at, is the Bayes solutions, the maximizing expected utility solutions, constitute a minimal complete class. All and only the forecasts that are probability forecasts are admissible, and no proper subset of them is a complete class. So you have the existence of the complete class and the instance that they're of Wald's theorem that they're all Bayes solutions. Now, in order to motivate finite additivity, I have to force some discontinuity in here, because that's what we're going to do. And I want to motivate this in the following way. The Breyer score is a proper score in the sense that it induces forecasts, if you're a Bayes agent, which is revealing of your opinion. That is, unlike Finetti's betting game, the forecasting game incentivizes straightforward response. If my probability for B is P, and hence for B complement is 1 minus P, I maximize my expected utility, minimize my expected loss on the Breyer score uniquely by announcing the pair P1 minus P. That is, I'm incentivized to be straightforward in the choice of my forecasts. This is different than you get in betting, where with betting there can be all kinds of reasons why I want to be strategic in the bets I announce. Finetti became interested in the scoring rules because they induced the same coherence conditions. You don't give incoherent forecasts, but the coherent forecasts are exactly the Bayes forecasts, and I'm incentivized to be straightforward in my forecasting. Now, the Bayes forecasts, the proper scoring rules are not restricted to the kind of continuous version of Breyer score that I just gave you. Let me motivate a discontinuous Breyer score in the following way. I'm a firm and I'm hiring an expert to give me a forecast with regard to a decision that rests on whether or not the event B is probability 1/2 or less than 1/2. I take one decision if the probability of B is greater than 1/2, and I take another decision if the probability is less than 1/2. And I want to not only use Breyer score, but I want to make sure my expert I'm eliciting from is attentive to the fact that I really want the expert to think hard about whether the forecast is more than 1/2 or less than 1/2 for P. And the way to do that is one way to do that is to modify the Breyer score by putting in an extra penalty for being on the wrong side of 1/2. And you can do this without violating the strict propriety of the scoring rule. And I've written up here a small version of the Breyer score with a penalty 1/2 on the wrong side, which takes the original Breyer score and adds 1/2 to the penalty whenever your forecast is on the wrong side of 1/2. And the idea is this is to incentivize the expert to be a bit more careful, because you're only going to get finitely many decimal places back, to be a bit more careful about giving me a forecast that drives me to the correct decision. So this is still a strictly proper scoring rule, but now the loss functions for the pure forecasts look like this. I've taken that original, let me skip a slide. So this is the same graph, but now for this modified scoring rule, you'll see there are some jumps in where the scores are, where the risks are. And let me just show you how this relates to the picture I was showing you before for the continuous one. So I'm skipping. So the pieces of the continuous one are broken up in those three regions because of the way the half enters. And what you get is the following. This is the region where the probability is going from 0 up to, but not including a half. Here is a half-half. And here is the region where the probabilities are at least a half and up to 1. The discontinuity is because on purpose we put in that break, that jump at a half. So over here is the remaining one piece of the boundary at a half-half. All these other regions, their lower boundary, when I put the pieces back together again, would fit above this region or above that region. So this lower boundary is half open, starting there, closed, open at that point. The half point has been jumped over there. This is open there and closed all the way down there. So what you get in terms of this discontinuity, and this is a problem that Wald had, is for this kind of loss function, you don't have a minimal complete class because the Bayes solutions, which consist still of this lower boundary here, this point here, which is the half-half point, and this lower boundary here, no longer constitute a complete class because if I take a point over here, it's dominated, but it's only dominated by other incoherent forecasts that are sitting out here. The half-half takes care of region in there, but all these forecasts, which are incoherent, that is, don't constitute probabilities, they sum to more than one, have dominators that are themselves incoherent. They used to be dominated in the continuous case by Bayes solutions over here, but because of the discontinuity, that's no longer the case. So this is a bit of a problem for Wald-type decision-making. There is no minimal complete class, and the Bayes solutions do not constitute a complete class. The Bayes solutions will not, for example, give you a decision that is making this option inadmissible. The ones that make this option admissible are other inadmissible options, but no admissible option makes that forecast inadmissible. So this is an example of a kind of problem that Wald had and explains why his theory builds in all kinds of continuity and compactness assumptions with regard to loss functions in order to get back to the existence of a complete, a minimal complete class, or where getting the Bayes solutions as a complete class. Let me stop here and make sure that the picture is motivating a problem about how do we handle discontinuous loss functions. And I introduced the discontinuous functions, loss functions, as based on the psychological consideration that I wanted to have an incentive for the expert that focused the expert on the critical value for my decision. So I'm paying the expert to give me information that's relevant to my decision, and I want the expert to be incentivized to be really careful about the critical probability that's going to be relevant for my decision. I'm coming pretty much out of time here, so let me wrap up and say what's going on. Well, so this is the discussion of the complete, minimal complete, and so on. Now, let me go back. You can see what I'm going to do. I don't have a last point there. I would like to have the a forecast whose value in risk is that point, because if I had that point and I had that point, then I would have that point collinear with that point, collinear with that point, and the admissible strategies would complete the missing lower boundary. Well, I can't do that with countably additive probabilities, but I can with merely finitely additive probabilities. So if you allow the forecaster to construct a mixed strategy that agglutinates its mass there and agglutinates its mass there, then I complete the missing lower boundary. And all these problems of discontinuity go away. And what you get by using finitely additive mixed strategies then is the following. I'm skipping over the details of this particular example, you get the following simplification of the entire theory. You don't need compactness assumptions, continuity assumptions. All you need is that the decision rules whose risk functions form a lower boundary. That is, if you have a decision problem with well-defined lower boundaries to the risk, then the lower boundary is accessible by these mixed strategies, and there always are a minimal class of admissible rules, and every one of them is a Bayes rule. So the problems that were plaguing Wald because of discontinuous decision problems rules go away completely. There's a minimax decision rule. You get the generalization of the minimax theorem to these infinite games now, and there's a least favorable Bayes rule, at least favorable prior. That would be the nature strategy. And then I'll stop here. There's a rationalizability theorem that you can prove using this extended minimax theorem. And let me put it this way. Assume that the loss function is bounded above and below, no continuity required, but there's in that sense a limit of worst and limit of best things that can happen to you. And if you take a decision rule that's not Bayes for any prior, that is, in the IP jargon, would be E inadmissible. So this is where I'm touching base with some of the IP theory. So if you have a decision problem with bounded loss above and below, but no continuity anywhere built in, infinite state space is perfectly fine. And you have an option which is E inadmissible against the vacuous prior. So you take the set of all distributions and find that there's no distribution which makes this decision rule Bayes, E admissible. Then there's a mixed strategy, a finitely additive mixed strategy that uniformly dominates. So we've gone back to requiring the Finetti standard of coherence, and we're saying, if it's not admissible, then I can produce the uniform dominator. So we can combine Wald's criteria of admissibility with Finetti standard of coherence and say, if you have a decision rule which is not admissible in Wald's sense, E admissible against the vacuous prior, then in fact there's a uniform dominator. And we've combined Wald and Finetti together. Neither of them may be happy with how we've done it, but we've combined Wald and Finetti together and used finitely additive priors to take Wald's standard and show how it applies for these decisions. I'm skipping the section which you can read here and say, there is a problem that remains, I won't hide it, that not every prior has a Bayes solution, but that I think we can bracket for this discussion. So let me summarize the second part. So the decision theoretic basis for trying to motivate finite, not countably additive probabilities using principle 4b as the version of countable additivity to be violated, the continuity condition, is that a failure of simple dominance, which I was saying looks like a defect in Finetti's theory, can be turned into lemonade by using mixed strategies that achieve the missing value, that is, get you out of the range of expectations that you get from countably additive probabilities. And that allows recovery of a theorem about minimal complete class of admissible decisions. There exists a minimal complete class. They're all and only the Bayes solutions. And the minimax rule still works, and you can get the minimax theorem applying to such cases. And so there's a minimax decision rule, which is Bayes. And under this, we get back to a harmonious unification of Wald and Finetti, in the sense that if you have a decision rule which is never Bayes, E inadmissible against all priors, then with this finitely additive mixed strategy, you have a uniform dominator. But I remind you, there is a price here. Lurking underneath this is a failure of the Fubini theorem, and not every prior has its Bayes rule. So the admissible, that bottom boundary doesn't constitute a set of all priors. It's only some priors that constitute the base selection. So I'm going to stop there and see if I've made any sense. And there's some references here and notes on the results about the improvement of Almer's, the modest improvement of Almer's result. I'm going to stop here